Greetings, and thank you for joining our presentation. Today, we're excited to share our project on ultrasonic welding robots for semiconductor bonding using ARM-based embedded systems. Our focus is on how ARM microcontrollers can enhance real-time control in ultrasonic welding, an increasingly vital process for miniaturized semiconductor manufacturing. As semiconductor devices become smaller and more fragile, achieving precise, low-damage bonding at low temperatures is critical. Our system bridges automation, energy efficiency, and precision. I'll let the participants introduce themselves.
This is Anne.
This is Farishta.
This is Francesca.
This is Zubeda.
And I am Chris Shiv. We were guided by our mentors Nick Richardson, Ryan Schneider, and Professor Sukumar.
This is an introduction slide as, let's say, now our project focuses, why it matters, and some of the key challenges that we study of traditional bonding methods face latency, energy, and control challenges that can lead to defects. Our project addresses the need for compact, adaptive systems that can handle real-time ultrasonic signal processing. By leveraging ARM Cortex architectures, we can reduce latency and improve process consistency.
When we looked into existing research on ultrasonic bonding, what stood out first was how essential it's become in semiconductor manufacturing. It is a method that lets you create solid connections at low temperatures, which is perfect for working with fragile or miniaturized chips. Studies from Tresky show that the strength of the bond really depends on how much ultrasonic energy you apply, the pressure, and the bonding time. Later on, researchers like Wong took it further by achieving room temperature bonding and even introducing real-time sensing, tracking things like impedance and resonance to monitor the quality of the weld as it happens. From a control systems perspective, we also noticed a shift towards using ARM-based embedded systems instead of traditional platforms like FPGAs or DSPs. ARM systems are not only relatively cheaper and more energy efficient, but they also offer strong real-time control and are highly programmable. That flexibility makes it easier to develop and modify control algorithms, fine-tune parameters, and integrate sensors, all without the steep learning curve or hardware constraints that come with other systems. This combination of precision and adaptability is what makes ARM-based control such a promising foundation for ultrasonic welding applications. But despite all these advances, we noticed a few major gaps. There still isn't a true closed-loop control framework that directly connects the ultrasonic signal features like vibration data with the actual reliability of the weld. Most of the data that's available is vendor-specific with no universal quality standards, and issues like latency and signal noise at high frequency are barely addressed in the literature. Sensor integration is another big missing piece. There's very little work combining things like force and vibration feedback into the welding process. Our project aims to bridge those gaps by using an ARM-based system for adaptive control. We're working on a real-time tuning of the welding parameters like frequency, amplitude, and force, while also building mappings between the vibration data and weld quality. The goal is to make the process smarter, faster, and more consistent, setting a foundation for future systems that can even predict or correct weld issues on their own.
On this slide, we have an overview of our system architecture and the technical framework that drives the ultrasonic welding process. Here's how our system operates. It begins with parameter configuration and pre-contact sensing. then transitions into ultrasonic activation, real-time feedback monitoring, and finally a cycle reset. The ARM Cortex-M handles slow power operation and streamlined processing, ideal for moderate performance tasks such as reading sensor inputs, performing lightweight filtering, and managing communication between system modules, while the Cortex-R is designed for high reliability and safety-critical control. This class offers deterministic response times and enhanced safety features, which are essential for high-precision robotic welding. This architecture allows us to continuously monitor and adjust welding conditions, creating a more intelligent, adaptive robotic system.
Alright, first let's watch a short video of the robotic welding simulation so you can see what's actually happening. As you just saw, the robot arm moves along a specific path from point P1 to P9 at a steady speed. This is exactly how it would work in real semiconductor factory. The arm-based controller manages the ultrasonic vibration, keeping everything stable and constant during welding. Sensors track things like vibration, temperature, and force, so the robot can adjust instantly if anything changes. This makes the welds clean, precise, and strong, way better than trying to do it manually. Basically, the simulation shows that combining robots with arm-based signal processing improves accuracy, speed, and reduces errors.
Conclusion and future work. A few takeaways. Ultrasonic welding is a clean and safe bonding method for semiconductors. This method doesn't use heat or solder, so it doesn't damage the delicate semiconductor parts. It's fast, energy efficient, and maintains the chip's electrical and structural properties. For example, thin gold or aluminum wires can be bonded to a chip bed without melting or harming the chip. Robots make the process faster, easier, and precise. Robots can position parts with very high accuracy and do the same task repeatedly without mistakes. They reduce human error and make the welding process more efficient and smoother. For example, a robotic arm can place semiconductor parts with micron-level precision every single time. ARM-based real-time control improves consistency by managing ultrasonic vibrations. The ARM-based system monitors the vibrations in real time. If anything changes, it adjusts instantly to keep the welding stable. Low temperature protects semiconductor materials. Because this process works at low temperatures, sensitive materials don't get damaged. This is very important for modern tiny chips. For example, the chip and bonding wires remain safe, unlike traditional soldering that could melt or warp them. Future work or recommendations: adding more sensors to improve accuracy and clarity. Adding sensors for force, vibration, and temperature helps the robot adjust the welding more precisely. This means fewer errors and better quality bonds. For example, extra sensors can detect if too much pressure is applied and automatically adjust to avoid damage. Use AI or machine learning to improve weld quality. AI can analyze sensor data and predict problems before they happen, automatically fixing them. This makes the bonds more consistent. For example, the system could warn engineers if a bond might fail and correct it without stopping the process. Connect the system to IoT platforms for monitoring and control from anywhere. For example, someone could check sensor readings and make changes from a laptop at home or in another building. Test the robot on real semiconductor parts in actual factory conditions. Simulations are great, but real testing is needed to make sure it works in real-life conditions. For example, using different chips and wires in a production line will show if the robot maintains accuracy in bond quality.
These are the works cited. We'd like to thank the ARM Institute, our mentor, and the Ohlone College Semiconductor Skills Bridge Academy for their support. The references listed include foundational studies from Tresky, Wong, Ishida, Brockman, and others that informed our design and simulation. Thank you for your attention, and we're happy to take any questions.